Thank you very much. It's, as ever, a great pleasure to be here in Lumini. So let me begin by thanking the organizers for their kind invitation and their charity in allowing me to give a talk. I have a personal philosophy, which is that when you give talks, everybody should get something out of them. And since I can't guarantee the mathematics is going to be any good, I bought some chocolates. And if you take one and circulate them,
what if I take them all?
You can take as many as you want. I don't want them back. But make a point of telling anyone who didn't come to the talk that there was chocolate.
Right.
Thank you. Okay, so what I want to do is to talk about a very simple problem, which is just to do with numbers that arise in circle packings, Apollonian circle packings. And so let me just write on the board what it's meant to be about. So the idea is the following. We start off with these things, which are Apollonian circle packings, which I'll describe in a moment. And they give you a bunch of numbers, and you want to describe these numbers. And these are the asymptotics and the distribution of the radii. They involve infinitely many circles. And since it doesn't sound like it has anything to do with the theme of the conference, let me just mention that the route to get there is to understand these circle packings in terms of a non-uniformly hyperbolic dynamical system. And then use that to deduce the asymptotics. Hyperbolic in this sense means expanding. Okay, but I'm talking particularly about circle packings because they're very easy to describe, but the same sort of basic principle works for other things. So let me try to, having squandered this board by writing like this, let me move on to the next one. So what I would like to do is just to remind you of how these circle packing guides kind of work. And it's something like the following. So this is by way of notation. And what we do is, the first step is we choose 4 circles in the plane. So choose 4 mutually tangent circles in the plane. This is R2. And so I use the notation that script C of 0 is the collection of these 4 circles, which are not surprisingly called C01, C02, C03, and C4. Whoops, wrong way around, yes. That way around. So there's just 4 circles, and so hopefully they look something like the following, except, of course, they're actually circular rather than this strange shape that I draw. So that's one of the circles. And then there will be another 3, and they're all meant to be mutually tangent. So the next one might be like that, which is almost circular. And then there'll be another guy down here, say, like that. And then the third one's the hardest one to draw. It's the one that's going to touch all 3 of these circles. So these are meant to be the 4 mutually tangent circles in the plane. Okay, so that's the first step. The second step is to draw more circles. And so we let the collection C of 1, this will be 4 more circles. So I'll denote them by C1, 1, C1, you've seen them all, C1, 2, C3, 1, C4, 1. This is going to be 4 more circles, which I will attempt to draw in a different color. And so these will be the, maybe these guys. So there'll be 1 inscribed inside here. And there'll be another one inside here. and another one here, almost a circle, and another guy over here. And since the colours are not so easy to see, I'll just shade them in a bit. And so these are the next 4 circles in this picture. Okay, and these just fit into the sort of curved triangles. So be circles inscribed, good word, inscribed into the 4 curved triangles, i.e. as in the picture. Okay, and you can just carry on in this this drilling vein, so you continue inductively or iteratively. Continue iteratively. And iteratively means that we build more and more circles, and so in particular there'll be a family called C of n at the nth level, and this will consist of perhaps 4 times 3 to the n minus 1, give or take me getting the indices correct, circles. And here n is going to be greater than or equal to 2. So far nothing very sophisticated has happened. The next level down, the C3 level, whoops, which I haven't done, would just be the 12 circles which correspond to this guy, this guy, this guy, this guy, except it shouldn't overlap, this one, this one. What am I missing? These guys probably. Down here, and maybe these guys as well. Okay, so you can keep doing these things, and this is, if you carry on ad infinitum, you get an Apollonian circle packing, and so I'll denote by just script C the union of all of these sets. So this is going to be the union n greater than whatever, maybe 0, of C of n. So this is the collection of all circles in this construction. So why are we interested in this? Well, there's some metric property to it as well. I want to say that if I have a circle somewhere in this construction, then I denote its radius in the following way. Have a radius which I will denote by R of C. So maybe that's a definition. Okay. So I'm constructing circles, and they have various radii, and the basic question is, how are these radii distributed? So question, how are these radii? That's the collection of numbers R of C, all possible radii for circles in this construction distributed, in whatever sense that means. Okay, so it's a reasonable question, a bit vague. Let me give you an example. So here's one. So if we start off with the first 4 circles having specific radii, so let's assume that, so this will be an example. If we assume that C of 0 has radii which are of the following form, maybe the outer circle will have radius 1, and the other 4 circles will have radius 1/2, 1/2, and the one that fits in would be 1/3, for example. So it doesn't look really like this picture is too accurate for that, but that might be the values of the first 4 guys. But then, of course, everything else is specified after that. So all the other radii are known. So the next one down would probably be the next 4 values, which are 1/3, 1/6, 1/6, and 1/15. And you can carry on in this spirit. So when you get down to C2, so these are the yellow circles in this picture, then they will also have radii which is specified just by your initial choices. And these have radii, and there'll be 12 of them. which according to my calculations are 1616, 1/11th, 1/11th, so I'm not counting them. I'm counting them with multiplicities, not suppressing that. 114, 114, and 1/15. Somehow there should be 12 of them. 1/23, 1/23, 1/35, 1/38, and another one which is 1/38. I think somehow I'm not going to do a second example since it's tedious enough doing one. So basically we just get a sequence of numbers, and the game is the following. We fix the first 4 radii so that it makes sense. We generate infinitely many numbers and we try to describe the statistics of these things. That's all we're trying to do, he says optimistically. Let me see if I can get this board to go up. Okay, so as you might imagine, if you choose the first 4 radii, then the rest are specified by some particular formula, which one can do using elementary calculus. And so let me just make this remark. And it says that there's a simple formula relating the radii of, let me call them something, maybe the radii of 4 tangent circles. Let me draw another picture maybe. So here is one circle, here is a second circle, here is a third circle, and there's the fourth one inside. And so the radii are just going to be R1, no particular order, R2, R3, and R4. Okay, and the formula between relating these things is the following, I think, which is 1/R1 plus 1/R2 plus 1/R3 plus 1/R4. And if you take this and you square it, it should be twice 1/R1 squared plus 1/R2 squared plus 1/R3 squared plus 1/R4 squared, assuming I got it correct. So it's a simple formula. And this simple formula, of course, you all recognize as being due to Descartes. And it appears in correspondence between Descartes and Princess Elizabeth of Bohemia. And all of this correspondence is online, at least the letters that weren't lost. And this is from November 1643. And Princess Elizabeth of Bohemia was the daughter of Queen Elizabeth of Bohemia, who had the good fortune or otherwise to be born in England. And in fact, she was educated at Combe Abbey, where we have dinners from Warwick. So you can go there and pay homage to the mother of this eminent mathematician, if you feel so inclined. And I'll leave it as an exercise for people who want to take up the challenge of checking it. I gave a talk once where I put this formula down, and Hillel Furstenberg asked me to write it down for him. So obviously he was having trouble proving it directly himself, but I'm sure it's up to the present audience. Okay, so this is a simple formula. So what results do we want to prove?
Do you know the poem?
Do I know what?
The poem.
I do know the poem. I'm not doing that. Yes, this is a reference to Frederick Soddy, the eminent Nobel laureate in chemistry from 1921, I believe, who wrote the poem of this formula, which I will not do. Okay, so let me talk about what the possible results are here. And I think maybe I will do the following. Maybe I will move one of these boards down. How about not that one? Let me try another board. How about the first one? And then I can move the other board up in a minute. And then rather than squandering it with large writing of no content, I can put the results on. Did something go somewhere? Is it really? So obviously I'm pushing the wrong button. That's always a giveaway. What else have we got? How about that one? Ah, yes, very good. It emerges majestically, almost. Okay, right. Okay, so let me say something about what we want to prove. So all we've got so far is a bunch of numbers. And one might like to say something about the properties of these numbers. And what one can prove is the following. So these are results. And so first of all, just observe that as you look at more and more circles, obviously the radius has to go down to 0 due to the fact they're all packed inside a fixed circle to start off with. And there is a theorem that tells you about how they tend to 0. And this theorem is due to, well, it's a counting theorem, counting. And it's due to Kontorovich and O. Kontorovich, if I spell it correctly. And O from 2009, possibly. And the theorem says the following, that you can find some constant, which I usually call C, but somehow there are too many C's around, so I'll call it K. Doesn't mean curvature. And there's some value delta, which happens to lie between 1 and 2. And this has the magic property that if you count the number of those circles in my collection, with the property that the radius of that circle is not too small, they tend to 0. So let's assume it's bigger than, say, 1 over t, for some value t that's going to get big. Then as t increases, so as t gets bigger, you allow more and more circles, 1 over t gets smaller, and so in particular this turns out to be asymptotic to k times something, t to the delta. So the number grows, and it grows at this particular polynomial rate. So of course that simply means that the limit, it's an m apparently, the limit as t tends to infinity of this number c in c such that r of c is greater than 1 over t. Well, this divided by t to the delta is equal to k. So since it's an erudite audience, I didn't need to write that, but I thought maybe I'd just throw it into...
Is this for all initial forces?
Yep, doesn't matter what you start with. I chose ones that actually had rational values. It makes no difference. Any real numbers, providing they start off mutually tangent, you get exactly the same asymptotic. So the value delta certainly doesn't depend on the original configuration. I'm hesitant about the k. Let me not be too specific about that. Okay, so where does the number delta come from in particular? Well, we have the following remark. Well, in fact, delta is a familiar number. It's simply the Hausdorff dimension of the Apollonian Circle packing. So I draw lots of circles up there. So if I took the union of all the circles in my construction and took the closure, this will be a kind of fractally thing. And this fractally thing has a Hausdorff dimension which is equal to delta. And apparently you can't say that real numbers are equal to strings of digits, but I will. So it's equal to 1.3057 plus some more terms, in fact. And this estimate's due to Kurt McMullen from 1998. Okay, so it grows at some particular rate, and this rate does not depend on the initial configuration of these things. And maybe I should mention a reference. So if you are interested in more pictures, there's a book by Kirillov, which is, so it's A-K-I-R-I, some number of L's, V, called A Tale of Two Fractals. And one of the fractals is indeed this circle packing. Okay, so that's some tosh about these things. So what I want to do is not talk about this result so much. What I would like to do is to talk about something else. So let me just swap the boards around again, if I can figure out which is which. How about that one? And let's try that one. Probably the wrong one. That's definitely the wrong one. Try that one. Ah, yes. Okay, so I want to talk about not so much just this counting estimate, but also about some other kind of thing. I'll make it a bit dark, but never mind. But I want to talk about another kind of statistics, which is a central limit theorem associated to the sequence of numbers. So one has to formulate something that makes sense and actually works. And so that brings us to the following formulation. So this is the theorem. And this is a kind of central limit theorem of some type. It's a bit dark, never mind. And this is joint work of myself and my good friend Mariusz Urbanski. And I gave a talk last year talking about another paper with Mariusz Urbanski, which was 131 pages. This one is currently work in progress, and it's only 97 pages. So, work in progress. And it's approximately 97 pages. Those of you who have been to Denton will realize there's not much else to do there but write papers. Okay, so what does the theorem say? It says essentially the following, assuming I state it correctly. Oh, I've written theorem twice, which is not so bright. It should say the following. First of all, we have a number which passes for some sort of average. And so let me say what that is. There's a limit. So the limit, which I will define to be the following. It's the limit as n tends to infinity of something. Well, what I do, well, n is the level at which I'm putting in the circles. So what I do is I look at all the circles at the nth level, at which there might be 4 times 3 to the n minus 1. And then I look at the logarithm of the radius of the circle, which looks suspiciously negative, and I compare that with n. But then I want to weight it by something, and then take an average. And so in particular, I want to rate it by the radius again, to the power delta. It's the same delta as up there. And then I normalize it, so I divide out by all the circles in my packing of this value again, r, c, delta. So the idea is that these radii are going down at some linear sort of rate on average. And the statement is that this limit exists, which may not look so great. And the central limit bit is because we want to compare these values, taking away something that looks like an average here. So the statistical bit says that we can find something that looks a bit like a variance, which I'll call sigma squared, for obvious reasons. And if I choose any values a and b, as one does in central limit type theorems, I can look at the following. I look at all the circles at the nth level of my packing. That gives me 4 times 3 to the n radii. So I look at the logarithm of that radius, and I compare it with this number. So that's minus n times a. And then I divide out by a square root. And I want to look at the circles for which this lies in a certain interval. So I put an indicator function. I'm afraid I was educated at Warwick, so my indicator functions are given by chi's, not bold-faced ones, which are also popular. But this is meant to be the indicator function for the interval AB. And then I probably have to put these weights in again, so that will be RC to the delta. And then I just have to normalize it. So I normalize it by the same quantity. So I sum up all the circles at the nth level, 4 times 3 to the n minus 1 of these guys RC to the delta. And the hope is that makes some sort of sense. And as we let n tends to infinity, there should be some limit. And this limit should be like a normal distribution. So my amateur status in writing down statistical properties is revealed by the fact I have to check what a normal distribution looks like. And according to my notes, it looks like minus t squared over 2 sigma squared dt, unless someone tells me it's not. Okay, so the result is telling us that these numbers, just a bunch of numbers tending to 0, so we take the logs, then it becomes a sequence of numbers, at least whose absolute value is tending to infinity, and the statistical properties of them are, well, they grow in a certain way, and you can also say something about their distribution of lengths compared with this typical value. So these are the two statements that I wanted to mention, and maybe I will now venture onto one of the sideboards and to make a couple of remarks. I think there's two remarks. So one thing I haven't said, but which probably most people know already, is this construction I've written down. Maybe I can bring one of these boards down a bit further. This construction that I've written down with all the circles at the top, well, the limit set that you get, the closure of all the circuits is circles, it's actually a limit set for Kleinian group if you think of the plane as being the complex plane and the upper half space being above it. So in fact, C is a limit set for a suitable Kleinian group. And in fact, the results that I've stated and the results I've stated generalize to other kind of limit sets of a similar nature. And the results generalize to other limit sets for Kleinian groups. And the second comment is the following. In fact, you don't have to just work with these sort of constructions. The actual method uses this dynamical system, which I'm yet to introduce, but in fact, you can use the same method to consider other things. So there are similar results for pre-images of points for parabolic rational maps. So if I have a parabolic rational map, T from C hat to itself, then the idea is that you can fix a point x0. You can look at all the points that map onto it. So T to the n of y is equal to x0. And then you can look at the logs of the derivatives of the map at the point y, which there will be a finite bunch of guys. And the statistics of these numbers will be rather similar to the ones up here, because the method of proof is exactly the same. And I will now explain what that is. So I've stated the simple geometric construction. I've stated a couple of results about this sequence of numbers. What I haven't told you is where the dynamical system is. You may be waiting for one, in which case your wait is over. So as it says in my notes, question, where is the dynamics? And every question should have an answer, and the answer to this is the following. So these are dynamics. So we start off with our four initial circles, and we want to generate our other circles by some sort of transformation. And the way we do that is to reflect in certain circles. But we don't use the circles we first thought of, we think of dual circles. So the first step is to define four dual circles. So we associate to the original circles, which I have deftly named C subscript 0, four more circles. And these I will call DI, D for dual, and they will be circles which are circles in the complex plane. All this sits in the complex plane, which are centered at some point called, say, Zi, and of radius Ri. And there's four of them. And they're defined by being dual to the previous 4 circles. What does that mean? It means that in my original picture, which looks like this, I had this circle almost touches, this circle and this circle around here. And then the dual circles are 4 more circles which go through the points of intersection, if I get them in the right order. So there'll be a big circle, which is hard to fit in, which will go through these 3 guys, and then it will go off. I'll cheat and make it more into an ellipse, like that. And then there will be another circle, which will come down here. It'll go through this point, that point, this point. Well, I missed that point, actually, never mind. And back again, and close up, as circles should do. And then there'll be another circle, which won't fit in at all, but it goes through these 3 points. And then there's one left over, which is going to be the circle in the middle, which goes through these 3 points. Like that. So these are the dual circles to the original 4, and in my notes they are labelled, for no particular reason, since I don't think I'll use them again, D1, D2, D3, and D4. Possibly the white and the yellow look too close in colour, making it slightly more confusing to see. Okay, so the construction of dual circles is not exactly new. It was proved by Beecroft in 1842, I believe. So it's not very topical, but it's useful in constructing a dynamical system which will generate the rest of these circles. I'm looking around for something to clean. I don't know. Maybe I will clean the remarks, since it's not doing very much. So step 1 is just to look at these 4 dual circles, but then we'd like to use these circles to define some sort of transformations. And so the second step is the following. So we associate to each circle a sort of reflection, so we can reflect, maybe invert in each of these circles, which are di, where I runs from 1 up to 4. And the way it's defined is it will be a map from the complex plane, suitably extended, to itself. And here's another challenge of notation. So the idea is that I take a point, and I think it might be Ri squared, Z conjugate minus Zi conjugate over absolute value of Z minus Zi squared plus Zi, or it might not be. But the principle is that if I have one of these nice yellow circles, then what does it mean to invert in the circle? Well, it means that if I have a point outside the circle, it goes inside, and it goes inside on a line which goes through the origin. So here is actually the center of this circle, which is Z of I. It's got radius R of I, and the transformation is one that takes a point outside, called Z, to a point inside, which I will call Ri of Z. So this is I equals 1, 2, 3, and 4. So I have 4 different transformations in the plane, which moves stuff around. And so this is great, but we'd like to have a single transformation, or at least a finite collection of transformations that do something useful. And I think maybe at this stage I will investigate the boards again. Let's try that one. So I'd like something that looks more like a sort of nonlinear hyperbolic kind of thing. So that one can come down, and then it will be an interesting discovery. Maybe it's that one. And possibly it's a bit dark at the front, so maybe I should try to get it down a bit further. Like that. Okay, so the next step is to combine these reflections to get maps which are going to do us more good. And so we do that in the following sort of way. And so this is the third step. So step 3. So let me let T be equal to the part of the circle packing. So the part of the circle packing inside D4, inside this guy. So there's some circle packing that's going to take place inside here, and that's the bit we want to concentrate on. So inside D4. So let me denote it by T. So it's all this stuff. Some complicated fractal stuff, and I'll call it T. It's just one piece of the construction. You do this for each of the pieces, but let me concentrate on this one. And then we can consider maps, 4 of them, I guess, maybe 3 of them. Phi I, which is going to be R4, which is a reflection in that circle, composed with Ri, and hopefully it goes the right way and maps T into T. So you have some stuff inside here, you reflect it in one of these 4 circles, it goes outside, and then you reflect it inside D4, it goes back inside. And it maps T onto itself. That's the plan. So that's I equals 1, 2, and 3. Of course, if you reflect the circle in itself, you go back where you started, so you don't want to have R4 composed with R4. That would be bad. And you can do similar things the other way around. And so what does that do for us? Well, the bit in the middle, this part, looks like a sort of curved triangle into which we have inscribed various circles, all of which I will not be able to draw, but they maybe look a bit like that. And what happens is, maybe to actually touch the boundary there, that would be nice. And so what should happen here is that we now have, on this region, which I've called T, it's this fractally thing, we have these 3 transformations called phi I, and each of them maps it to itself. So for example, there are going to be 1, 2, 3 points, which are just these guys. And what happens is that each of these maps the region T to itself, but it pushes stuff up into one of the 3 corners. So in particular, let me call this guy x1, I'll call this guy x2, and this guy x3. And then what happens is that this will be a fixed point for one of the maps, x1, phi 1 maybe, and this will be a fixed point for another map, and this will be a fixed point for the other remaining map, which is phi 3, which is probably invisible to almost everybody, probably everybody. And then the game here is that what does the picture look like? So for example, we have the following, that if you apply phi 1, then what happens is that this fractally shape gets scrunched up into that corner. So in particular, if this was the circle, then the image of this thing gets squeezed up into this region. So here is x1, this is the region T, and this image here is going to be phi 1 of T. And phi 1 is basically a contraction, except at the fixed point x1, which is indifferent. It's a parabolic point. So let me just find somewhere appropriate to write all this stuff, and maybe I will write it on that one. So we have, after all of this shenanigans, we've ended up with, a good word, shenanigans, we've ended up with a triangle, or a fractally shape. It's just a compact metric space. And we're mapping it into itself by one of 3 maps, but whichever map we choose, it fixes one of the corners, and it strictly contracts except at the fixed point. So summarizing that, so the maps phi I all map this region in the middle to itself, and they are contracting. And they're strictly contracting except at the point of the fixed point, so except at the fixed point, which which is xi. And this is true for I equals 1, 2, and 3. So we're interested in studying the distribution of the lengths of these circles. At the moment, I'm only concentrating on this particular piece. Of course, there are circles hiding in the other regions, but we could just treat those in a similar way. And my skills at drawing and exposition will not allow me to do all of them at the same time, so let me just concentrate on the ones in the middle. And so if you have any kind of dynamical system which has an indifferent fixed point, but is contracting everywhere else, you may be inclined to do what I'm about to do, which is to induce in some way, or iterate something, or try to live with the hyperbolicity in a nice way. So we can associate now a countable family. Because when it was finite, it was also countable, but this is going to be an infinite countable family of uniform contractions and if you're used to thinking of continued fractions and theory transformations, it's just what you think it should be. You iterate one of the branches, and then eventually when you get bored, you go to the next one, and that gives you the hyperbolicity. So the uniform contractions might be psi, and these will be of the form, you iterate one of the maps lots of times. Maybe I'm doing this the wrong way around, we'll find out in a minute. Composed by some other guy. And this is for different branches, I not equal to j, and where n, I guess, is greater than or equal to 1. So you keep shoving stuff up into the corner, and then you flip it by just applying one of the other branches, and it turns out to be uniformly hyperbolic. I'm looking at the clock in the desperate hope I'll be saved from giving too much of the proof. Vivian will bail me out, I'm sure. An act of charity. Okay. So how does any of this help us? Well, it would be kind of helpful if this dynamical system actually allowed us to keep track of the circles that we're trying to understand, we're trying to enumerate in some particular way. And this is indeed the hope. And so the idea is that in the original picture, right in the middle, we had a nice friendly circle, which is one of these guys, this guy. So he's so friendly, I'm going to do him in a more hashed form. So this guy would have been, I think, C1, 1, no I. So it's just one of the circles in my construction. And assuming I got this halfway right, which is almost the same as being right, then we can write most of the other circles in the generation for this family, all the other circles appearing in the Apollonian Circle packing, or but maybe finitely many, in the following form. So in T, the circles can be written in a special form, in the form, what form would that be? Well, we take the circle we just thought of, which is going to be this guy, C1, 1, this guy in the middle, but then we're going to apply which is the same as this guy here. He's too ashamed to say his name, but he's also C1, 1, this guy. And so what we can do is we can get the other circles going down here by applying the appropriate transformation, and then we get the ones that are hiding in the other corners by flipping these things over. So using a rather gruesome notation, we can write this in the form maybe phi I1 N1. So we apply one of the transformations lots of times, and it will be phi I2 N2. I write plus 1 because I need it for simplifying my notation. So it will be phi I3 N3 plus 1, and we keep on going. And then we get down to, when we get bored, which is IK, NK plus 1 applied to that circle. So I shuffle the circle around by combining different of these parabolic maps, whichever works for me, and I get this composition. But since I know that I have something of that form, I get something hyperbolic, then I can hopefully rewrite this as, perhaps, phi I1 N1 composed phi I2 by borrowing one of these. That's why I put an M2 plus 1 up there, into there, and then I can compose this with phi I2 to the n2 composed phi I3 composed stuff. And then somewhere near the end I get perhaps phi nk minus 1, ik minus 1, composed with phi ik. I always need another of the parabolic maps to keep me honest, to make it hyperbolic, and then the stuff that's left over will be phi ik nk. All I've done is group these things together in a slightly different way, and then the claim is that I can write this down to here as just appropriate hyperbolic maps on the same domain. So for no particular reason, I'll call this psi x1, psi x2. It's meant to be a psi, it's becoming a chi for some reason. Psi x1, and then this guy would be psi, whatever works for the indices. How about maybe it's xk minus 1, something like that. So the circles are now generated by a countable family of suitably hyperbolic maps. Okay, so that's great. So now we have a hyperbolic dynamical system of some kind, and it's generating all of these circles. And what we'd like to do is to play with the numbers. We'd like to maybe count them, or maybe we'd like to get some sort of central limit theorem like at the top. And so we need to do something, and at this stage, the cavalry rides in, because we're going to talk about transfer operators. There's always a sigh of relief with me when we get onto transfer operators. Perhaps the rest of the audience may not share this enthusiasm. But the proofs of the theorem just depends on some sort of analysis. So if you're going to prove some sort of central limit theorem, then your options are manifold and manifest. There's lots of them. But since it's a sort of central limit theorem that doesn't involve measures too much, it's kind of useful to have something that involves transfer operators, an operator-based proof. So let me just say this is to do with the proofs of the theorems. And it says in my notes, the proofs are now straightforward. So I should thank you for attention and say goodbye, but maybe I will actually add a few more lines in.
Reach 95 pages and the rest is 2 pages?
Actually, most of the 95 pages is my co-author's enthusiasm for writing. Yes, okay. Well, there's not. I don't think I can answer that as accurately as I should do. Let me not go into too much detail. So let me just say how we could do it, or how we do it, in fact. And the way is to use some sort of symbolic dynamics, which is not essential, but at least it's a familiar thing. So we can associate a space, which is going to be a countable state, subshift, which obviously just corresponds to this bunch of contractions on the space D. And there's a natural map pi from this sequence space onto T, which is going to be a Holder continuous. It's a semi-conjugacy for the shift, so Holder continuous. Because it would be Holder continuous if I told you what the metric was, but you have to guess that one. And there's also a Banach space, which I'll denote by H alpha, and this is going to be a space of Holder continuous functions, well, alpha Holder continuous functions, G from sigma into R. These functions are really just locally Holder continuous because you shouldn't really have Holder continuous functions on countable state things. It makes life too difficult. But the principle is more or less the same. And then we can associate to this setup a suitable transfer operator. And the transfer operator is what you think it might be. So this is by way of a definition. And the definition is we define a transfer operator. And it's called L subscript S. Many years ago, I used to call them Renewal operators, but then Renewal complained, so I don't do that anymore. And the way they're defined is ls of g. So I take a function which is on my subshift of finite type, and at a point x, it's just given by, it's a one-sided subshift. I sum up over all the points that shift onto my particular point x, and then one of these maps has to make an appearance. So it comes in through a derivative. So let me put y0 prime, and this will be pi of x all to the power s. So here I guess y is really a sequence yn, n goes from 0 to infinity in this shift space, and so y0 is just the first coordinate telling me which of these contractions I'm dealing with, and probably there should be a g in there as well. That would be nice, wouldn't it? G of y. And so here I haven't said what alpha is, but it's just something that works. So for some alpha between 0 and 1. And I haven't said what s is, but it's a complex number, and I want that the real part of s should not be too small. So to make the thing converge, because it's a countable sum, it should be bigger than something, and this something is fortunately smaller than the value of delta. So this is the sort of tool that gets you to do things, and the good news about these operators is that they are quasi-compact on the space of Holder continuous functions. So L of S is quasi-compact, which allows you to prove anything you want, basically. So let me, I have exactly, well, my co-author needs 97 pages. I've got the proof down to, both theorems down to 8 lines. Let me see how much of it I actually need. I'll try and trim it down during the next stage. Let me get rid of step 3. So let me just give you a reproof, an alternative proof of theorem 1, the counting result, which is a theorem due to Kontorovich and O. So their proof uses lots of stuff about spectral theory inclining groups, but in fact you can prove it just using this transfer operator stuff. So here is an alternative proof of the counting result. That's a bit hard to read. So the counting theorem. Usually I make a joke about theorems that count, but at the moment I don't really have time. So we can study, should have a sign up there that says applause or laugh or something. That'd be good. We can study the series, which is given by the following. So we define something looking like a Poincare series. So we sum up over all the circles in our configuration, and we sum up the radii to the power s, where s is a complex variable. And we can study this by comparing it with something else, by comparing with well, what we compare it with is our operator, because it's the only thing we have. We sum it n equals 1 to infinity, applied to a suitable function, might be 1, in fact, and so applied to a suitable function, and what we get is a complex function which converges in a half plane, and it has a pole at the value s equals delta, and then you can just apply a Tiberian theorem. So the properties of eta of s imply the asymptotic formula, and the way to get there is just to look up some Tauberian theorem, a piece of machinery that gets you from complex analysis into asymptotic stuff in a rather easy way. And the proof of the central limit theorem type result is basically the following. Well, you just look at the characteristic function, that is a Fourier transform associated to the distribution, and you study it using, indeed, a transfer operator. So we consider, well, maybe we just write the characteristic function or Fourier transform in terms of in terms of something. And in my notes it says in terms of the operator L to the n, well, S has now become delta, the real value, minus IT over root n. And then we're back with one of the classical proofs of the central limit theorem, and the result follows just by perturbation theory on the maximal eigenvalue. And use perturbation theory on the maximal eigenvalue. And then you're done. So in both cases, the proofs are very straightforward, and Vivian thinks I'm about to finish. She's probably right. So that's it, in fact. I have another page left, which was only there in case I didn't manage to get to the end in the right time. So I think I'll finish there. Thank you very much.